2,000 kilometers of tracks cut through the Taklamakan Desert. This line slices through billions of tons of sand. 12,000 workers spent 10 years here. Even American engineers noted the determination. But this is just the beginning. How did they overcome fierce sandstorms and heat? The environment offers no respite. President Xi Jinping's government invested over $3.5 billion. This funded the world's longest railway network. One can notice tracks in the dunes. It seems simple, but in reality, it is a symbol of modern engineering. Protective barriers rise visibly against the wind. Everything only gets more complicated. The railway stands finished, ready for use. 127,000 square miles of sand cover the Taklamakan Desert, isolating the Xinjiang region and Tarim Basin. For decades, this land remained a blank space on the map, split by two mountain ranges. Why would engineers attempt to breach such a hostile environment? Surface temperatures in summer exceed 160 degrees Fahrenheit, while winter drops to minus 13 degrees Fahrenheit. Hidden beneath this unforgiving sea of dunes lie billions of tons of untapped energy, including oil, coal, and rare earth elements. One can notice how heat haze distorts the horizon over the dunes. But this is just the beginning. China had to undertake what was once considered impossible to unlock these resources. At first glance, construction here seems feasible, but in reality, there is no solid foundation to build upon. One can observe that the ground consists entirely of shifting sand, with no water or electricity available. The challenges only get more complex further on. 890 kilometers of track form the Hotan-Rokyang Railway. It completes the Taklamakan Desert Loop, a circular network extending 2,685 kilometers along the southern edge. Completed in June 2022, it stands as the longest desert railway in the world. It is visible how the steel line cuts through the landscape. How do you choose a route across a landscape that never stops moving? Before a single bridge was built, this question demanded a solution. Thousands of wind measurements determine the route across a landscape that never stops moving. Why spend months living deep in the desert for surveys? High-resolution satellite imagery and ground-penetrating radar offer an initial map, but only physical presence confirms the prevailing wind directions, dune movement, and zones of relatively stable ground. Survey teams drilled hundreds of boreholes, some tens of meters deep, to study the layers beneath the sand. But this is just the beginning. The investigation is only gaining momentum. One can notice how technicians place every route marker by hand. At first glance, the sand looks identical everywhere, but in reality, specific coordinates are recorded with centimeter-level precision to ensure absolute accuracy. The line had to avoid wind corridors where sandstorms could sweep away entire trains. However, the route must remain close enough to access oil and coal fields along the Tarim Basin. This meticulous planning transforms what was once a blank, white space on the map. A steel curve now wraps around the desert. 140 degrees Fahrenheit is the blistering heat under which hundreds of local farmers gathered to tackle a critical task. Before the steel curve could wrap around the desert, the shifting terrain required immediate stabilization to support the future railway. They bundled straw, dry twigs, and thin bamboo into long sheaves to mechanically anchor the sand. But this is just the beginning of the process. Why arrange these simple organic materials in a specific geometric pattern? To the untrained eye, it looks like a primitive agricultural method unsuitable for industrial engineering. Farmers utilize this layout because it breaks the wind's direct flow, scattering its force in different directions to protect the surface. They planted the sheaves deep into the ground in a strict checkerboard pattern. One can notice how every square is aligned diagonally at 45 degrees instead of in straight lines. At first glance, the task seems simple. But in reality, exact precision is required to force the sand to settle within each grid. Each square measured exactly 1 square meter, creating a trap for airborne particles that would otherwise displace the dunes. Workers covered every planted bundle with an extra layer of twigs to ensure the structure held firm against the elements. It gets more complex further on. One can see the first few grids spreading across the horizon, forming thousands of organic sand fences that stretch to the farthest dunes. After several months, these straw checkerboards blanketed hundreds of acres, transforming the environment visually and physically. The landscape turned from shifting dunes into a fixed patchwork of golden brown and green as the ground hardened. The sand stopped moving, creating a solid crust capable of supporting significant weight. Consequently, heavy trucks could finally drive across the surface without sinking. It is visible how the massive desert construction commenced on this newly stabilized foundation. The project moved forward on secure ground. Hundreds of bulldozers mobilized to flatten the dunes after the sand surface stabilizes. The machines cut down high ridges and redistribute the material into lower areas to create a smooth, balanced surface. Surveyors rigorously check elevation and slope to ensure uniformity across miles of open desert. One can notice how conveyor systems push excess sand away from the work zone, while compactors gently press the top layer to form a firm foundation. But this is just the beginning. Why is it necessary to inject water into the loose surface of the dunes? Dry sand inherently lacks the cohesion to support heavy construction machinery. Engineers discovered that moisture helps bind the grains together, creating a significantly denser and more cohesive layer. Using long sprinkler arms and underground pipes, they spray controlled amounts of groundwater across the site, allowing the liquid to penetrate several inches deep. Once the sand reaches the right level of dampness, heavy rollers move in to remove air pockets. It is visible how the steel drums lock the particles in place, turning soft, shifting sand into a firm base with every rotation. The constant rumble echoes across the desert as the ground compacts. By the time the surface dries under the sun, it has hardened enough to carry the weight of cranes, mixers, and supply trucks, forming a solid foundation built from nothing but sand and water. It does not end at this stage. At first glance, the compacted sand seems ready for use, but in reality, it requires a base layer of soil to remain stable. Dump trucks pour out loads of reddish earth onto the surface. Bulldozers then push and level this material across the area to seal the work. This layer adds weight to the sand below, strengthening the surface against shifting under heat or vibration. Thus, a dense, stable base is formed to support the first stages of construction, 11,000 bridge piers, exactly the number of supports required to span the vast emptiness of the desert. Why do engineers drill through dozens of feet of loose sand before laying a single foundation? It would seem simpler to build upon the surface crust, but in reality, without reaching the solid gravel or compact soil beneath, the shifting dunes would compromise the structural integrity of the entire line. Reinforced concrete pile drivers operate day and night using steel casing pipes to penetrate this unstable layer. Workers begin the process by stabilizing the ground base. To ensure the boreholes do not collapse under the pressure of the sand, the team pumps in bentonite slurry. Concrete is then poured from the bottom up through tremie pipes to prevent the formation of dangerous air pockets. At first glance, lowering the steel cages seems like a routine mechanical task, but in reality, they must be positioned with millimeter precision, as even the slightest misalignment could cause the pile to tilt. 130 degrees Fahrenheit is the difference between daytime and nighttime temperatures in this harsh environment. Because of this extreme fluctuation, construction crews work mostly at night when the wind is calm and the sandstorms ease. One can notice how the railway's foundations seem to grow roots deep into the desert sands, thanks to these steel and concrete piles. But this is just the beginning. On top of these foundations, the bridge piers begin to rise. Row after row, a vast concrete forest stretches across the desert, consisting of shafts between 16 and 50 feet tall. These are cast using slip-form molds and reinforced with galvanized steel containing salt-resistant additives to withstand the corrosive climate. The short, uniform spans between piers are designed to minimize the effects of wind and extreme temperature changes. As the sun sets behind the Kunlun Mountains, the endless lines of pillars stretch toward the horizon, resembling a skeleton of steel and concrete unshaken by the winds. It gets more complex further on. Thousands of pre-stressed concrete box girders are lifted into place using heavy crawler cranes or self-launching gantries. Each girder measures over 100 feet long and weighs several hundred tons. Specialized flatbed rail cars transport these massive components before they are hoisted one by one onto the piers. Laser precision is required to align the girders, keeping tolerances within just a few millimeters to ensure a perfect track. Once the spans are secured, crews pour the bridge deck slabs or install precast concrete panels to form a smooth surface. It is visible how every span is spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. From above, one can see that more than 65% of the Houghton-Rokyang Railway, 310 miles, runs on these elevated viaducts. The structure appears like a silver ribbon cutting across an ocean of gold, a living monument to human ingenuity against one of Earth's harshest landscapes. 260 feet is the length of the steel rails prepared for installation against one of Earth's harshest landscapes. Next, the team installs concrete blocks known as sleepers evenly along the track bed. Why is the precise alignment of these blocks so critical? At first glance, laying concrete ties appears to be a routine structural task. But without exact positioning, they cannot effectively distribute the weight of passing trains or prevent the track from shifting. Workers align each sleeper, then use a lifting frame to lower the heavy rails onto them. Once fixed and fastened, the system prevents bending under heavy loads. But this is just the beginning. Specialized cranes hoist the massive steel sections into place, carefully aligning them along the center line. One can notice how crews adjust every joint and gap to allow smooth expansion under the intense desert heat. They tighten the fastening clips that lock the rails onto the concrete base, completing hundreds of miles of track over 11 months of continuous work. It gets more complex further on. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load tested with trains weighing thousands of tons. It seems obvious that the heavy construction is stable, but in reality, engineers verify safety with extreme rigor. Results showed elevation deviations of only a few millimeters, even after hundreds of test runs. The elevated design allows natural airflow to sweep beneath the viaducts. It is visible how this prevents sand from accumulating on the tracks. Therefore, all operational data flows to the control center through IoT sensors and solar-powered cameras monitoring every section in real time. After 6 months of rigorous testing, the Houghton-Rokyang Railway officially opened in June 2022. This marked the completion of the 1,685-mile loop circling the Tuk Lake. The line is now fully integrated into the transport network. 122 degrees Fahrenheit is the searing heat that construction crews endured while carving a path through the unforgiving landscape. Why force a highway through the violent sandstorms and shifting dunes of the Taklamakan Desert? At first glance, the project appears to be a futile struggle against nature, destined to be buried by sand. But this ambitious infrastructure was critical to link the two oasis cities of Luntai and Minfeng, cutting directly through the desert's core for more than 300 kilometers. Work officially began in 1993 and progressed rapidly despite the harsh conditions. By October 4, 1995, after just over 2 years of intense labor, the road was opened. The total cost reached an estimated 1,750 million yuan, or roughly 260 million US dollars. But this is just the beginning. The asphalt surface hides a complex engineering secret beneath. One can notice how the road resists the constant pressure of the environment without buckling. A multi-layer foundation of gravel, straw mats, and geotextiles acts as a shield against the elements. These materials are specifically designed to stop the drifting sands from burying the route, ensuring the connection remains open. Because the area ranks among the highest in solar radiation globally, receiving more than 2,700 hours of sunlight each year, engineers turned the scorching sun into an asset. Along the highway, which stretches for more than 436 kilometers, they installed 86 solar-powered pumping stations. Hundreds of photovoltaic panels at each station capture the energy. It gets more complex further on. The captured energy powers pumps that draw groundwater from depths of over 100 meters. Water travels through an elaborate underground pipeline network rather than evaporating on the surface. Using precise drip irrigation technology, the system distributes moisture to more than 200,000 trees lining the highway. They survive in a region that receives almost no rainfall, creating a green corridor. As a result, the route has become the world's first carbon-free desert expressway, where electricity produces water and water sustains life. Everything only gets more complicated. One can observe how this infrastructure now supports more than just transport. The highway connects isolated solar farms and scientific research outposts, while acting as a passage for ecotourism. What was once the Sea of Death is transforming into one of the world's largest ecological laboratories. Since transportation became more accessible, tourism in the desert has begun to thrive. Along the edges of the Taklamakan and Gobi deserts, vast man-made forests and water reservoirs have been developed into parks. Community-based tourism is growing here, blending ecotourism with Uyghur and Mongolian cultural heritage. Visitors can join camel riding tours that cross the sands. Transition to the next level. It is visible how travelers pass over rolling dunes that resemble ocean waves during these excursions. The tours last anywhere from 2 to 5 hours, depending on the specific route chosen, and stop at rest areas set up in the middle of the sands. Each trip costs between 40 and 120 US dollars. The Taklamakan Desert today stands as proof of ecological restoration, combining conservation with real-world experience. Hundreds of kilometers of steel tracks cut through the shifting dunes, establishing a permanent line across the scorching sands. One can notice how the railway bridges rise above the heat haze, standing firm against constant wind erosion. This construction demonstrates that complex industrial engineering can function within a harsh environment, but this is just the beginning. Why undertake such a colossal project in a practically uninhabitable void? It seems illogical to pave a path here, but this infrastructure connects two previously isolated economic shores. Engineers utilize reinforced concrete and high-grade steel to resist the extreme thermal fluctuations found in the desert. At first glance, the bridge piers seem like simple static supports, but in reality, they are calculated anchors in a sea of moving sand. It is visible how the structure defies the natural landscape, turning a barren wasteland into a functional transport corridor. From raw materials like cement and metal, a complex system emerges. And this is not the limit. The railway remains as a tangible testament to engineering intelligence.